Alright, in this video we're going to look through a few examples of applying our three kinematics equations to problem solving. And specifically we're just going to look at one dimension for now. We'll get to 2 dimensions soon. First thing you want to do when you're solving a problem is draw a picture as you read through the problem. So here we know a kitten is trapped on the roof of Samina's shed, so I should draw a shed here. And there's a kitten on top. There it is. Draw some whiskers on maybe. Your kittens don't have to look like kittens, it can just look like a blob, that's fine. There it is. The shed is 4 meters above the ground, so that height above the ground here is 4 meters. She has some physics superpowers, so she can jump 4 meters straight up. That's very impressive. So here she is. She's going to jump straight up with some sort of a V1Y. She's going to go up, come down, and land right beside the kitten. And she wants to make sure her landing is soft. So her V2Y, she wants to be 1.5 meters per second. She wants that to be down though. So really important to draw myself a little coordinate system saying that y is positive in the up direction. If this was 2 dimensions, I'd also say x is positive forward, but I don't need that because I just have 1 dimension. If y is positive in the upwards direction, then a velocity that's moving down must be negative. There's actually another piece of information that's in here which isn't maybe apparent. We can see the numbers, right? I've put the numbers on my picture. But if Samina is free falling, right? She's just going through the air. She doesn't feel any forces other than gravity during that part, which means that she's going to have an acceleration due to gravity. So her acceleration is in the y direction. It's going to be negative 9.8 meters per second squared. That's Samina's acceleration during that whole flight. That's the acceleration of any object regardless of its mass that's sort of free falling. Great. So that's our nice picture. The next thing you want to do is write down everything you're given because that'll kind of help you organize what you know and see which equations you need to use. So I'll just go through each of them. I know AY, the acceleration, is negative 9.8 meters per second squared. I know V2Y is negative 1.5 meters per second. I know y1, so Samina starts out on the ground, right? So her initial height is 0, and y2, she's going to end up with the cat up here. So her final height above the ground is 4.0 meters. The next thing I want to write down is my required, so what am I looking for? And I'm trying to solve for her initial velocity, so that's v1y. Looking at my given and required here, one thing that stands out is that I don't have any information about time. So that means that probably the first and second kinematics equations wouldn't be the right way to go. The third one doesn't have time in it, so that's a really good one to use here. So we will. So our third kinematics equation is that v2y squared is equal to v1y squared plus 2ay y2 minus y1. Great. I'm going to rearrange this for v1y, that's what I want to find. So I'll move this entire term to the other side. It's being added here, so it'll be subtracted on that side. So v2y squared minus 2ay y2 minus y1 is equal to v1y squared. Next thing I want to do is get rid of that squared. So I'm going to square root both sides. That square root cancels my squared on this side. That square root does not cancel that squared, right, because they're subtracting in there. Then I'll just rewrite it forwards. So v1y is going to be the square root of v2y squared minus 2ay y2 minus y1. And we're all rearranged for what we want. So that means I can just plug all my numbers in and I'm good to go. So first, starting with v2y, that's the negative 1.5 meters per second. That's squared. I have 2 times ay is negative 9.8. y2 is 4. y1 is 0. So we've got that all in there. I can just plug it all into my calculator to get my v1. So I like to start with this piece. So I have my negative 2 times negative 9.8, that's going to be positive, so I might as well just make them positive right away. Times 4 minus 0, just times 4. So this whole term is positive 78.4. That's going to be added to the negative 1.5 squared. I'm not even worrying about putting the negative sign in there just because it happens to be getting squared, so it's going to end up positive. So under my square root altogether, I have 80.65. Just want to square root that. and I get 8.98. Let's take a look at sig figs. I only have 2 sig figs in everything here. So that means I'm going to use 2 sig figs in my final answer, which will be 9.0. So that 8 rounds that up to a 0, or 9.0. And the units of velocity are meters per second. That's v1y. And pretty obvious from our picture, she needs to jump up. That's going to be the direction is up. She jumps down. That's not going to work very well. So definitely that's the direction is up. And that's it. Next example is a little bit trickier. So here we're going to have 2 objects, or 2 people, Abby and Brenda. They're walking to physics class. So here's Abby. A for Abby here. And here's Brenda. And Abby is initially at rest, so I'm actually going to write her given information just down right underneath her. So we know her initial velocity, so v1 in the x direction of Abby is 0. She's initially at rest. Brenda, on the other hand, is walking at a constant speed. So the velocity in the x direction of Brenda is 1.7 meters per second, and that's positive because I'm going to define forwards to be positive here. So I'm going to write in my little x is positive on my picture. Now Brenda is initially 5.6 meters ahead of Abby. So that means if I set Abby to have an x1 of 0, then that means Brenda, x1 of Brenda will be 5.6 meters. All right. Abby decides to catch up to Brenda, so she starts accelerating forward. So she's going to have some acceleration of Abby in the x direction here. And the acceleration, A, of Abby in the x direction is a positive 0.91 meters per second squared. That's this one here. We want to know how long does it take for Abby to be side by side with Brenda. We know one more thing about Brenda, and that's that her acceleration is 0. She's going at constant speed, right? So no acceleration there. Okay, what we're looking for, so our required is delta t. That's the same for both of them. We want to know delta t at the moment when the x2 of Abby equals the x2 of Brenda. So I'm trying to find time when their final positions are equal. When you're in this kind of situation, it's a good idea to make an equation for the final position of Abby and an equation for the final position of Brenda, and then we'll set them equal to each other, and that will let us solve for time. So I'll show you what that looks like. I'll make Abby's equation over here. So this is Abby. Her final position, so x2 of Abby is going to be, I'll just write up my second kinematics equation, x1 of Abby plus v1 of Abby delta t in the x direction plus a half a of Abby in the x direction delta t squared. Let's see if there's anything I can simplify here, right? I know that x1 is 0, so any terms that are 0 you can just get rid of right away. I also know that v1 of Abby is 0, so that whole term is gone. That means that Abby's equation simplifies to x2 of Abby is just a half times the acceleration of Abby in the x direction times the time squared. That is the x2 of Abby. Next we're going to do the x2 of Brenda here. And we can actually use the same kinematics equation for Brenda. The second kinematics equation for constant acceleration works for somebody who is constantly not accelerating too, someone that has an acceleration of 0. So x2 of Brenda is going to be her x1 plus her initial velocity, which is actually just her velocity in the x direction times delta t, plus a half the acceleration of Brenda times delta t squared. So we can clean this up as well because Brenda's acceleration is 0. This whole term is gone. And the x2 of Brenda simplifies to just her x1 plus Oh, I put a half in here. I'm so sorry. I was just getting ahead of myself in the equation. There is no half there. My apologies. Plus her velocity. So velocity of Brenda in the x direction times delta t. I actually don't even need to write the v1 here, just because for Brenda, her velocity is constant. So her initial velocity is equal to her final velocity. It's just velocity. She's not accelerating. Okay, I've got a nice equation for the final position of Abby and the final position of Brenda. What I want to know is the delta t at the moment when those two are equal to each other. So I'm going to actually set x2 of Abby equal to my x2 of Brenda. That means I'm going to write out Abby's equation here, the half acceleration of Abby delta t squared. Say that equals the x2 of Brenda. That's the x1 of Brenda plus the velocity of Brenda times delta t. This looks actually a lot like a quadratic, right? It's got a delta t squared in it, it's got a delta t, and I'm trying to solve for that delta t. When you run into a quadratic equation like this one, to solve it, it's actually okay to put numbers in right away. That's because for quadratic, when you do the quadratic equation, doing it with variables gets really, really messy. So this is one exception to our always rearrange with variables first rule. When you're dealing with a quadratic equation, it's okay to put numbers in early. So that's what I'm going to do. So I have a half times Abby's acceleration here, which is the 0.91, times delta t squared. That's going to equal the initial position of Brenda, which is 5.6, plus the velocity of Brenda, which is 1.7, times delta t. I'm going to move everything to one side. It doesn't matter which side you move everything to. Maybe I'll toss it on the left just for fun. So move those guys over. I'll have the half times 0.91 delta t squared. Then this becomes negative minus 1.7 delta t minus 5.6. That'll equal 0. Just clean this up a little bit. Half times 0.91 is 0.455 delta t squared minus 1.7 delta t minus 5.6 equals 0. What I have is a nice quadratic equation. In my quadratic equation, this part here is a, this with the negative sign is b, and this is c here. So I'll write out my quadratic equation. There's a little song for it if you know the song. It's that delta t, the variable we want, equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There it is. Okay, we can plug in our numbers. So that'll be delta t will equal negative b, so b is negative 1.7. Negative negative is a positive 1.7. That'll be plus or minus the square root of b squared, so the negative 1.7 squared, minus 4 times a is the 0.455, c is negative 5.6, all divided by 2 times a, 0.455. All right, let's simplify the inside of that square root. It's just kind of messy there. So the negative 1.7 squared, I don't have to put my negative into the calculator because I'm just squaring that one, minus 4 times the 0.455 times negative 5.6. That negative really matters. That gives me 13.082 under the square root. So delta t is 1.7 plus or minus the square root of 13.082. On the bottom, I have 2 times 0.455. That's going to be 0.91 there on the bottom. So 0.91 on the bottom. All right. My next job is just to plug these into my calculator and see what I get. So I'll do the 1.7. I'll do the positive one first, plus the square root of 13.082, all divided by 0.91. That gives me a delta t of 5.8 seconds. Then I'll do the minus 1.7 minus the square root of 13.082 divided by 0.91. Delta t is also negative 2.1 seconds. Then we just have to look at these two answers. Mathematically, they're both solutions to this quadratic, but only one of them makes sense in real life. I'm looking for the time when Abby and Brenda are side by side. That time has to be positive. There's no such thing as negative time. So that must be my answer, positive 5.8 seconds. All right, let's do one that's similar but in the vertical direction. So here, I have Newton climbing a tree. So here's a tree. Make it nice and tall for my picture. There we go. It's got an apple on it too. So there's a little apple hanging from the top. And Newton decides, he wants to climb up this tree. He starts out on the ground and he starts moving upwards with a velocity. So the velocity of Newton in the y direction is 1.2 meters per second. The apple starts out not moving, but then falls as soon as he leaves the ground, and it's free falling, right? So the acceleration of the apple will be negative 9.8 meters per second squared. We're curious about how high Newton is above the ground at the moment when the apple bops him on the head. So this is very similar to the last question. So I'm going to write down my given information. So given for Newton and the apple separately. So first Newton here, and then the apple I'll do over here. All right, so for Newton, I know his initial position. So y1 for Newton is 0. He starts on the ground. I know his velocity. The velocity in the y direction for Newton is positive 1.2 meters per second. I should really put that on my picture, that up is positive here, so I'll add that. And I know the acceleration of Newton. So ay for Newton is 0. He's moving at constant velocity, right? So he's not speeding up or slowing down. The apple, on the other hand, starts at a height of 25 meters. So the apple starts 25 meters above Newton. So y1 of the apple is 25 meters. The initial velocity of the apple is 0. So it's initially just at rest, right, on the tree. And then it starts to accelerate downwards. So ay of the apple is negative 9.8 meters per second squared. All right. What I'm curious about is how high Newton is above the ground at the moment when the apple and Newton are in the same location. This is a very similar problem to the last one. I'm looking at the moment when x or y2 of Newton is equal to y2 of the apple. All right, so that means I'm going to make an equation for y2 of Newton, an equation for y2 of the apple, and then I'm going to set them equal to each other just like I did last time, and I'll solve for the time again, but this time I'm going to go one step further, use that time to find out how high Newton is off the ground. That's actually a really easy last step. The hard part is sort of all the whole quadratic equation business, getting this ready. So I make an equation for y2 of Newton, and I just use my second kinematics equation, because it's nice when it's already rearranged for that. So v1 in the y direction of Newton times delta t plus a half ay of Newton times delta t squared. I'll simplify this. Newton's not accelerating, so that part is gone. Also, Newton starts out on the ground, so that term is gone too. So the y2 of Newton is just his velocity, which I don't even need to write the 1 down because it's constant, times delta t. Let's do the same thing for the apple. So the y2 of the apple is going to be y1 of the apple plus v1 y of the apple times delta t plus a half ay of the apple delta t squared. What's 0 here? In this case, v1 of the apple is 0. The other terms are not. So I have y2 of the apple is y1 of the apple plus a half ay of the apple delta t squared. My next move is to set that y2 of Newton equal to my y2 of the apple. So I'll set this equation for y2 of Newton, vy of Newton delta t equal to y2 of the apple, y1 of the apple plus a half ay delta t squared. Again, this is a quadratic equation, so it's going to make more sense to solve this by plugging numbers in. So that's what I'm going to do next. The velocity of Newton is 1.2, and that's times delta t. And that equals the initial height of the apple, that's 25, plus a half times the acceleration of the apple, that's negative 9.8, times delta t squared. I'll simplify things a little bit, so I've got 1.2 delta t. It's equal to 25 plus a half times negative 9.8 is negative 4.9 delta t squared. To solve this quadratic, I'm just going to use the quadratic formula. So I need to put everything on one side. Maybe I'll put everything on the left side. So that gives me positive 4.9 delta t squared plus the 1.2 delta t minus 25. Right when it crosses over, it becomes negative, and that equals 0. So I use my quadratic formula. Delta t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So delta t is going to be negative b, negative 1.2, plus or minus the square root of b squared, 1.2 squared, minus 4 times a, 4.9, times c, negative 25, all divided by 2 times a, the 4.9. Let's plug everything under that square root into our calculator. So the 1.2 squared minus 4 times 4.9 times negative 25. That gives me 491 under my square root. So I have delta t is negative 1.2 plus or minus the square root of 491.44 all over 2 times 4.9, which is 9.8. Okay, let's toss these numbers in then. So I'll start with the negative. So negative 1.2 minus 491. I forgot the square root. Negative 1.2 minus the square root of 491.44 divided by 9.8. That gives me a negative time. So delta t is negative 2.4 seconds. Not very likely the right time. Now we'll do the positive. Negative 1.2 plus the square root of 491.44 and divide that by 9.8 and I get a positive time. Delta t is positive 2.1 seconds. If you tend to like clear your calculator a lot, then just write out a bunch of decimals, so 2.1396 seconds. Because we're going to use that time to calculate something else, I'm just going to leave the number in my calculator, not clear it, so that I can use it in a minute. Because I'm not actually done at this stage. The last problem I just had to find time. In this problem, I have to find height. How high is Newton above the ground? Fortunately, we already made a really nice equation for Newton's height above the ground as a function of time. So y2 for Newton is just the velocity in the y direction of Newton times delta t. It's already rearranged, I just have to plug in my numbers. So I can put in the velocity of Newton, which is 1.2, the time, which is 2.1396 seconds. So I just multiply by 1.2, and I get the height of Newton above the ground. Y2 is 2.56, that's going to round off to 2.6 meters with my sig figs, and we're done.